Let's see one more example with type variables and constraints. Here's our container type, polymorphic container, just like before, and let's write two functions to parse a piece of syntax into a container. Parse int will take syntax and create a container of int. So if the syntax has an integer, is an integer, then parse that and make a container. And otherwise error. And let's also do parse string. Great. What if we try to combine these two into one parse function? Parse, which takes in syntax and returns container of anything. There we go. Well, we've got a type error. And the problem is that these functions are adding a constraint. When we do syntax to integer, that's now a bin of int. And this wildcard A gets filled in with int and we're stuck. We can no longer return bin of string in the second branch. One way to fix this is to abstract over the function that we have. So instead of syntax integer, we write f. And f is going to take in syntax and give us back some A to fill in the container. And now we can use parse to parse ints and strings as long as we pass in the right helper functions. So now we have something that type checks, but it's not particularly useful. It's got two cases inside of a cond, but only one case makes sense at any time. And it's the case that matches up with the f that we happen to pass in. So let's rewrite this function. Instead of taking just an f, let's take in a predicate to say which case we're in. And then the cond inside needs only one case. And we can write the two parse functions down below. So for parse int, we need syntax is integer. And for string, syntax is string. Okay, good. Let's parse an int. Let's parse a string. So what we've done here with parse is we've abstracted over the parts that were common in our two functions up above, and we've got parameters to fill in the things that were different. And this way we can use our polymorphic value container in two different ways.